segment that I'm preparing for describing the change of element type in beams and shell problems. Okay, so let me start with a very simple beam problem. Okay, we're gonna draw a line. Okay, right there. Let's just put some dimensions here, although totally irrelevant for the problem, but I'll make this thing 10 inches. Okay, and exit. This is going to be my my beam. Okay, which is under different load, axial loading, perhaps bending, etc. Now, because I did this thing as a sketch and it's not a wireframe, I need to join it, otherwise I cannot actually mesh it with beam elements. Okay, so we did it. Let's apply some material on it. Aluminum on it. Very good, we're done. So now we're going to go to generative structure analysis right there, and we're going to mesh it with beam elements over here, beam element. And since the cross section of this is irrelevant as far as the present video is concerned, let's make it a circle. Apply a 1D property on that. Okay, and it's cylindrical beam. In other words, the cross section is a solid circle. And let's make it the radius as 0.5 so that we can see something on the screen right there. Okay, that's fine. All right, now let me take the left end of this thing to be clamped. Okay, good, and the right end of it to have a load in the downward direction. Okay, right there in the direction Z, so minus 100 pounds. Okay, there. All right, right there. It's not a big deal. We can run this, no problem, and it's going to bend. Here, it's going to bend as we expect. Let me change this thing to average ISO, although because of my graphics card this is not working. I'll make it simple. How about that? All right. Okay, now if you go here and you put the cursor on this 1D mesh and right click and you go down there, it says change element, change type. Okay, if you click on it, this opens up. It says, do you want this thing to be a beam or do you want it to be a bar? The difference between a beam and a bar is what you know from your strength of material class. Another beam beam will bend, bar will only actually either go in tension or compression. So let me say that I'm going to change this thing to bar and then say okay. All right. A couple of things is going to happen. When you go there and you double click on this, notice that this says well, first of all, if I try to run it, there's going to be a problem. Let me try to run this thing, see what the problem is. You see, it says that, wait a minute, you are giving me beam property, but you're saying that this is a bar element. So obviously, okay, it's not going to work. Just look. Okay, look, zero displacement. Okay, so first thing I'm going to do is I'm going to go here and I'm going to change this thing to bar. Let me deactivate this plot first. Let me deactivate this. Deactivate. Okay. We go to the property. We change this thing to bar. and then you click on this wrench. For a bar, all you need is the cross-sectional area. So if I set 0.5, let's see now, 0.5, 0.5 times 0.5, 0.25 times pi is going to be around 0.7, 0.8 inch squared. Okay, well, 0.5 times 0.5 times 3.145. Okay, there is the value. Okay, good. Now, the only problem is when I say OK here. All right, let's try to run it. Let's try to run it. All right, we didn't get that error message anymore, but look, the force is down, and we declare this thing to be bar, and when we look at deflection, we see 0, because a bar does not see a bending load. Okay. However, if I actually went and changed this load in the direction, change it to Y, for example, and 0 in Z, this is axial load, and if I run it, there won't be a problem. There you can see that it actually deflected, or you can make it negative, it puts it into compression. Okay, so this is how you changed a beam element to a bar element. And in fact, if I actually went and applied, let's do the following. Let's go and apply. Just keep in mind that the tip deflection was this thing it's very tiny, of course. You can see that. It's very tiny because this is a thick bar on the 100 pounds, doesn't deflect anything. But my point is that if you go here and you even put some 100 pound in a different direction so that it's not under axial load anymore. See this? What did I do here? Wait a minute. Let's see for a second. Vertex 100 pound in X, 100 pound in Y. So it's at an angle, 45-degree angle basically. You can see that. All right. Now when I run this thing, it's only going to see the component that makes it go into compression. It will not see the component of the force that actually make it bend. If you look at the deflection, you see that you get exactly the same number as before. Didn't change. All right. Don't let these small numbers bother you, because this was basically diameter 1 inch and 100 pounds on it, which is nothing. Now, I want to show you the same thing that you can do with shell elements. Okay, so let's actually get rid of this. And well, might as well use this. Okay, so let's go ahead and extrude this in direction X. Let's make it, I don't know, maybe 5 inches. There. Okay, so now we have a plate. So let's see now. Let's apply material. We have it. We have aluminum on this. That's okay. So now we're going to go to generative structure analysis. It's a plate, so we have to measure it ourselves. Right there. Okay. It really doesn't matter what the size is, because I just want to explain to you what the concept is. Okay. So we clamp this edge, and we apply a pressure, let's say a force, downward force here, right there, in the direction Z. Okay, downward force minus 100. Again, very small. 100 pounds on that edge. Okay, you can see that right there. Let me hide this line for you. All right, let's give it a cross section, thickness, 0.1 thickness, okay, 0.1 inch, about 2 millimeters. Now, not a big deal. We can run this. And it's going to work. And the plate is going to bend. There. Now let's hope that the graphics card does not, okay, with deflection there's no problem. It looks like this, no problem. 7 inches downward. These numbers don't have any significance. Okay, so let me go ahead and first of all deactivate this. Deactivate this plot. And you go here, you select this octave triangle mesh, right click, and again it says change type. Now notice that the type that we have is shell, which is the one that you just used. We have membrane, and we have shear panel. So membrane and shear panels basically do not see any out of plane bending. Okay, so for example, let me change it to membrane. Let me say okay. Now if I run this thing, see the load is down, which made the shell to bend, but let's run this thing and see what happens. Let's look at the deflection. 0. Don't let these colors fool you. Look at the number. It's 10 to the minus 9, 10 to the minus 19, 10 to the minus 20. 0 for all practical purposes. Okay? If you look at the stress, they're all going to be also... Oh, wait a minute. What was the direction of the load? Let me see for a second. Cancel. Z was down. Yeah. Okay, so this is all nonsense. Okay, these are all zero stresses, zero deflection. So in a sense, now let me go ahead and change the load here to be in the direction, for example, in plane direction, X and Y. So let's, instead of Z, which gives you 0, because membrane and shear panel do not see bending, okay? They're all in plane forces. So let's make it in the direction Y, 1,000, no, 100, and run it. And if you look at the, for example, the translation, well, I mean, these are meaningful, more meaningful numbers. If you look at the stress, deactivate this, and look at the stress. Let me change the scale here. Default. Okay, there we are. And notice that the deformation is only in the plane. If you look at the view from the side, you see? Right. So if your sheet metal only experiences in-plane loading or in-plane deformation because of the nature of the loading, or because of the way this is used in service condition, then you don't have to use shell. You can use membranes, okay? And membranes are more efficient because the number of degrees of freedom, there is no rotation, and etc. So let me show you another case. So this was a membrane. So let's go ahead and apply. Let's delete this load. Delete it. There is my plate, and let's apply a moment to that. A moment right there. A moment about that. Okay. Some value about the x-axis, which causes bending. Don't worry about the actual number. We're just gonna run it. Again, you're gonna see Pretty much zero stress and zero deformation. Let's see now. There's your translation. Minus 21, minus 21. This is all garbage. It's all round off nonsense. Okay? And if you deactivate this and look at the stress, they're all going to be pretty much zero, 10 to the minus 15 psi. It's zero for all practical purposes. Okay? Let's do another case. Let me change this thing, delete it. Now, well, okay, so let's actually change this type to back to shell and run it. You see that it's no longer zero. Look at the deformation. Definitely it's going to bend. Okay, they're still small because of the value of the load that I put in there, but I want to show you something. Let's look at the change the scale. There, see that? And with the stress, again, small numbers, but not zero for sure. Okay, so let me change the scale on the stress. Where is that? Scale on the plot. So if you have membranes with that, this does not deform. But if you have a shell, it will deform. So that's the difference between membrane and shells and shear panel. And you can do that through right-clicking and change it to type. Okay? In the case of beams, you also have to do the material, the property, because property for beam, you have to specify the whether it's a bar or it's a circle, etc. And for the bar, you just give the cross-sectional area. For shell, it's just the thickness. All right. I hope that clarifies